Hello, and welcome to Bedtime Science. Before we begin tonight's journey, take a moment to gently support the channel by liking the video and subscribing if you haven't already. It helps more curious minds find their way here, and it allows us to keep exploring the quiet wonders of the universe together. And while you're settling in, I'd love to know, where in the world are you watching or listening from tonight? Maybe you're tucked under blankets somewhere on the other side of the planet, or perhaps you're listening during a late evening in a city filled with lights. Wherever you are, the fascinating thing is that the same laws of physics govern your world and the tiny invisible world of atoms all around you. Because tonight, we're exploring something that exists everywhere, in your room, in your body, in the stars, yet behaves in ways that seem almost impossible. Tonight's topic is the surprising truth about quantum physics. For most of human history, the universe seemed reassuringly predictable. Objects moved along clear paths. Causes led to effects. The same rules applied everywhere, from falling apples to orbiting planets. These laws, described by thinkers like Isaac Newton, gave us a universe that behaved almost like a perfectly engineered machine. But about a century ago, physicists began to notice something unsettling. When they looked closely enough, far smaller than anything our eyes could ever see, the universe stopped behaving like a machine at all. Instead, it began behaving like something else entirely. Particles that could exist in multiple places at once. Objects that seemed to influence each other across vast distances instantly. Events that could only be predicted as probabilities rather than certainties. The deeper scientists looked, the stranger the universe appeared. At the smaller scales of reality, nature seemed to operate according to rules that defy everyday intuition. Rules that are still puzzling physicists today. And yet, despite how strange it all sounds, quantum physics works. Its equations predict experimental results with astonishing accuracy. In fact, it is one of the most successful scientific theories ever created. Quantum mechanics powers the technologies we use every day. From smartphones and lasers to the computers that run the modern world, it explains the structure of atoms, the chemistry of life, and even the nuclear reactions that allow stars to shine. But understanding how it works, and what it truly says about reality, is another matter entirely. Tonight we're going to take a slow and thoughtful journey through the story of quantum physics. We'll explore the moment classical physics began to crack. We'll meet the scientists, both famous and less widely known, who helped reveal this hidden layer of reality. And along the way, we'll encounter some of the most surprising ideas ever proposed in science. Ideas about particles that behave like waves, universes that may split into many possibilities, and the possibility that the universe itself might be built from information. But don't worry, we'll take our time. This is bedtime science after all, so settle in somewhere comfortable. Let the noise of the day fade away, and together we'll begin exploring one of the most mysterious and beautiful discoveries humanity has ever made. The strange and surprising world of quantum physics. For a long time, the universe appeared reassuringly simple. If you dropped a stone, it fell to the ground. If you pushed a cart, it rolled forward. If you looked up at the night sky, the planets traced predictable paths across the darkness. By the 19th century, many scientists believed they had discovered the deep rules behind all of these motions. The world seemed understandable, governed by elegant laws that could predict almost everything. At the centre of this worldview stood the work of an English mathematician and physicist named Isaac Newton. Newton's laws of motion, first published in 1687 in his book Philosophia Naturalis Principia Mathematica, described how objects move under the influence of forces. These laws explained falling apples, cannonballs, pendulums, and even the motion of the moon around the Earth. Newton also introduced the law of universal gravitation, which describes how every object in the universe attracts every other object through gravity. The strength of that attraction depends on the masses of the objects and the distance between them. In clear-spoken terms, the rule says that the gravitational force between two objects equals the gravitational constant, multiplied by the mass of the first object multiplied by the mass of the second object, divided by the square of the distance between their centres. That simple relationship allowed scientists to calculate planetary motions with astonishing precision. It was powerful enough to predict eclipses decades in advance and to chart the movements of distant worlds. For more than 2 centuries, Newton's framework seemed almost perfect. Then, in the 19th century, another great piece of the puzzle fell into place. A Scottish physicist named James Clerk Maxwell unified the study of electricity and magnetism into a single framework called electromagnetism. His equations revealed that electric and magnetic fields are deeply connected and can propagate through space as waves. Those waves turned out to be something very familiar. They were light. Maxwell showed that visible light, radio waves, and other forms of radiation were all expressions of the same electromagnetic phenomenon. Light itself was simply a ripple, travelling through electromagnetic fields at an extraordinary speed of roughly 300,000 kilometers per second. The mathematical elegance of Maxwell's equations was breathtaking. With just a few relationships between electric and magnetic fields, they could describe radio transmission, the behaviour of charged particles, and the entire spectrum of electromagnetic radiation. By the late 1800s, physics appeared to be reaching a state of comfortable completion. Many leading scientists believed the essential laws of nature had already been discovered. What remained, they thought, were smaller details, refinements, slight adjustments to known theories. One often quoted remark from the era captured the mood quite well. The physicist Albert Michelson, who would later win a Nobel Prize, suggested that the future truths of physics might already be contained within the 6th decimal place. In other words, the big mysteries seemed solved. But history has a quiet habit of surprising people who believe they understand everything. Even while confidence in classical physics was growing, small cracks were beginning to appear. Some experiments produced results that did not quite match the predictions of established theory. The differences were subtle, sometimes dismissed as experimental error or minor imperfections in measurement. Yet over time, those small discrepancies began to accumulate. Meanwhile, a brilliant French mathematician named Henri Poincaré was exploring a different problem that would later prove strangely prophetic. Poincaré studied the behaviour of systems that followed perfectly deterministic laws. In other words, systems where the future could, in principle, be calculated exactly from the present. But his work on what we now call dynamical systems revealed something unexpected. Even when the underlying laws were completely deterministic, the resulting behaviour could still become incredibly complicated. Tiny differences in starting conditions could grow dramatically over time, producing outcomes that were extremely difficult to predict. This idea later became part of what we now call chaos theory, although that term would not become popular until many decades later. Poincaré's insight did not overturn classical physics, but it hinted at something important. The universe might follow clear mathematical rules, yet still behave in ways that surprise us. Around the same time, experimental physicists were uncovering puzzles of their own. Laboratories across Europe were studying the behaviour of heat, radiation, and electrical phenomena with increasingly precise instruments. As measurements improved, certain results refused to align neatly with classical predictions. One particularly troublesome puzzle involved objects that had been heated until they glowed. When a metal object becomes hot enough, it begins to emit light. First, a dull red glow appears, then orange, then yellow, and eventually a brilliant white. Physicists studying this process measured how much energy such objects emitted at different wavelengths of light. According to classical physics, the amount of radiation at shorter wavelengths should increase without limit as the wavelength became smaller. In theory, an object should emit enormous amounts of energy in the ultraviolet region of the spectrum. But real experiments stubbornly disagreed. Actual measurements showed that the radiation peaked at a certain wavelength and then dropped off sharply at higher frequencies. This contradiction became known as the ultraviolet catastrophe, and it was anything but a small detail. Classical physics predicted an explosion of energy that simply did not exist in reality. Other experiments revealed similarly puzzling behaviour. The structure of atoms was poorly understood, and observations of atomic spectra showed sharp lines of colour rather than continuous ranges of wavelengths. Classical theory struggled to explain why atoms emitted only certain specific frequencies of light. Each of these anomalies seemed small on its own, but together they hinted that something deeper was wrong. The laws that work so beautifully for planets, pendulums, and projectiles seemed to falter when applied to the tiny world of atoms and radiation. Nature, it appeared, might follow different rules at very small scales. This realization introduced a profound philosophical question that still echoes through modern physics. When we write down the equations that describe the world, are we capturing reality itself, Or are we constructing mathematical tools that merely help us organize our observations? Classical physics had always carried an implicit assumption that its equations described a real and objective universe. Objects possess definite positions, definite velocities, and definite properties at all times. But as the 19th century drew to a close, that comfortable picture was beginning to wobble. The universe at microscopic scales was preparing to reveal a set of behaviors so strange that even the greatest scientists of the time would struggle to accept them. And the discoveries that followed would show that reality, when examined closely enough, is far more surprising than anyone had imagined. Toward the end of the 19th century, physicists were becoming extremely skilled at measuring light and heat. Laboratories across Europe were filled with carefully built instruments designed to study radiation, temperature, and energy. One of the most important questions concerned something known as blackbody radiation. A blackbody is an idealized object that absorbs every bit of light or radiation that strikes it. Nothing reflects away, nothing passes through. All incoming energy is absorbed. If such an object is heated, it begins to glow. At lower temperatures, the glow appears dull red. As the temperature rises, the color gradually shifts through orange and yellow, eventually becoming white and then bluish-white. This behavior is familiar in everyday life. The heating element inside an electric stove glows red when it warms up. The filament of a traditional incandescent light bulb shines white-hot when electricity passes through it. But physicists wanted to understand this glow with mathematical precision. They asked a simple-sounding question. If an object absorbs and emits radiation perfectly, how much energy should it radiate at each wavelength of light? In the late 1800s, scientists such as Gustav Kirchhoff and Joseph Stefan had already made important discoveries about thermal radiation. Stefan found that the total energy radiated by a hot object increases rapidly with temperature. His work was later given a theoretical explanation by Ludwig Boltzmann, resulting in what is now called the Stefan-Boltzmann law. This law states that the total energy emitted by a hot object is proportional to the fourth power of its temperature. That relationship worked beautifully when predicting the overall brightness of glowing objects. But the deeper question remained unanswered. How exactly was that energy distributed across different wavelengths of light? To solve this problem, physicists attempted to apply classical thermodynamics and electromagnetic theory. These theories treated energy as something that could vary smoothly and continuously. Unfortunately, when those classical ideas were used to calculate blackbody radiation, they produced an absurd result. According to the classical model, the amount of radiation should grow dramatically as the wavelength becomes shorter. In other words, objects should emit more and more energy at higher frequencies. The calculations predicted that the energy output would increase without limit in the ultraviolet region of the spectrum. This prediction quickly became known as the ultraviolet catastrophe. The name was not chosen lightly. If the classical theory were correct, any warm object would radiate enormous amounts of ultraviolet energy. In reality, nothing of the sort occurs. Careful experiments showed that the radiation from heated objects rises to a peak at a particular wavelength and then drops off at shorter wavelengths. Instead of an infinite explosion of energy, the radiation curve forms a smooth hill. The classical equations simply did not match the data. Physicists found themselves in a strange position. The most successful theories of the 19th century were failing in a very specific situation. This puzzle attracted the attention of a German physicist named Max Planck. Planck was a highly respected theoretical physicist working in Berlin. His interests included thermodynamics and the statistical behavior of energy systems. At first, Planck approached the blackbody problem using traditional physics. He attempted to derive a formula that would reproduce the observed radiation curve while remaining consistent with classical theory. But again and again, the calculations refused to cooperate. Eventually, in the year 1900, Planck tried something unusual. Instead of assuming that energy could vary continuously, he proposed that energy might be exchanged in tiny discrete portions. He suggested that energy could only be emitted or absorbed in specific packets, each packet having a size related to the frequency of the radiation. In words, his proposal stated that the energy of a radiation packet equals Planck's constant, multiplied by the frequency of the radiation. Planck's constant is an extremely small number. Its value is roughly 6.626 times 10 to the minus 34 joule-seconds. That number is so tiny that energy appears continuous in everyday life. The packets are simply too small to notice at large scales. But at the microscopic level, these discrete units of energy become important. Planck called these packets energy quanta. Using this assumption, he derived a formula that perfectly matched the observed blackbody radiation curve. For the first time, the theoretical prediction lined up with experimental measurements across the entire spectrum. It was an astonishing success. Yet the most surprising part of the story is how cautiously Planck treated his own discovery. He did not initially believe that energy truly came in discrete chunks. Instead, he viewed the idea as a convenient mathematical trick that allowed the equations to work. Planck hoped that a deeper classical explanation might eventually emerge, one that would restore continuity to the laws of physics. In other words, he suspected the quantization might simply be a temporary placeholder. History would prove otherwise. Around the same time, another German scientist named Walther Nernst was exploring related questions about thermodynamics and energy equilibrium. Nernst is best known for formulating what became the third law of thermodynamics, which describes how the entropy of a system approaches a constant value as temperature approaches absolute zero. Although Nernst's work did not directly introduce quantum theory, it helped shape the broader understanding of how energy behaves in systems approaching equilibrium. His research emphasized that energy distribution within physical systems follows very specific statistical rules. These ideas contributed to a growing realization that classical thermodynamics might require modification when applied to extremely small systems. When Planck's quantum hypothesis entered the discussion, it provided a new tool for thinking about energy exchange. The most radical aspect of Planck's proposal was not simply the mathematics, it was the idea of discontinuity. Classical physics had always assumed that quantities such as energy, position, and motion change smoothly. If a pendulum swings, its energy varies continuously. If a ball rolls down a hill, its speed increases gradually. But Planck's hypothesis suggested that, at very small scales, energy behaves more like the steps of a staircase. Instead of sliding smoothly between values, energy jumps from one discrete level to another. The difference between those levels is incredibly small, which is why everyday objects still appear continuous. Yet the underlying structure of nature may be fundamentally granular. At the time, very few scientists realized how revolutionary this idea would become. Planck himself viewed it as a modest adjustment designed to solve a specific technical problem. But that modest adjustment quietly introduced an entirely new principle into physics. Energy, it seemed, might not flow like water in a stream. Instead, it might arrive in tiny, indivisible droplets. And once that possibility entered the scientific imagination, the door to the quantum world had begun to open. At the beginning of the 20th century, the understanding of light seemed firmly settled. For decades, physicists had accepted the explanation provided by James Clerk Maxwell, whose electromagnetic theory described light as a wave moving through space. According to Maxwell's equations, light was an oscillation of electric and magnetic fields, travelling at a constant speed of about 300,000 kilometers per second. This wave theory had been enormously successful. It explained reflection in mirrors, refraction in lenses, and the beautiful interference patterns seen when light passed through narrow openings. Experiments performed in the early 1800s by the English scientist Thomas Young had already demonstrated that light behaves like a wave. In Young's famous double-slit experiment, light passing through two narrow slits produced a pattern of bright and dark bands on a screen. These bands were the result of wave interference, the same phenomenon that occurs when ripples on the surface of water overlap. Later, the French physicist Augustin Jean Fresnel expanded this wave theory with precise mathematical descriptions of diffraction and interference. By the late 1800s, the wave nature of light seemed undeniable. And yet, once again, careful experiments began to reveal something puzzling. Physicists studying how light interacts with matter noticed an effect that did not fit comfortably within the wave model. When certain metals were illuminated by light, they released tiny charged particles known as electrons. This phenomenon became known as the photoelectric effect. The basic setup was simple. A clean metal surface was placed inside a sealed vacuum tube. Light was directed onto the metal, and sensitive instruments measured whether electrons were ejected from the surface. If light behaved purely as a wave, classical electromagnetic theory made a clear prediction. Increasing the brightness of the light should gradually supply more energy to the electrons in the metal. Eventually, the electrons would accumulate enough energy to escape. In that picture, even dim light should eventually knock electrons free, provided one waited long enough. But the experiments told a very different story. A German physicist named Philipp Lenard, who had been studying cathode rays and electron behavior, performed careful measurements of the photoelectric effect around the turn of the century. Lenard discovered several strange and stubborn facts. First, electrons were emitted almost instantly when light of certain frequencies struck the metal surface. There was no waiting period while the electrons slowly gathered energy. Second, the energy of the emitted electrons depended on the frequency of the incoming light, not on its brightness. This meant that increasing the intensity of the light produced more electrons, but it did not make the electrons more energetic. Even more surprising, if the frequency of the light fell below a certain threshold, no electrons were emitted at all. No matter how bright the light became, nothing happened. These results were extremely difficult to explain using the wave theory of light. If light energy was spread smoothly across a wavefront, as Maxwell's equation suggested, then increasing the intensity should increase the energy delivered to electrons. Yet the experiments clearly showed that brightness alone did not determine whether electrons escaped. Something else was controlling the process. In the year 1905, a young physicist named Albert Einstein offered a bold explanation. Einstein proposed that light does not always behave as a continuous wave. Instead, he suggested that light sometimes acts as if it were made of tiny localized packets of energy. Each packet would carry a specific amount of energy determined by the frequency of the light. In clear-spoken terms, Einstein proposed that the energy of each light packet equals Planck's constant, multiplied by the frequency of the light. This idea built directly on the quantum concept introduced earlier by Max Planck. However, Einstein took the idea much further. Planck had suggested that energy exchange between matter and radiation might occur in discrete units. Einstein proposed something even more radical. Perhaps the radiation itself existed as individual packets. These packets of light later became known as photons. In Einstein's explanation of the photoelectric effect, each photon carried a specific amount of energy. When a photon struck an electron inside a metal atom, it transferred its energy in a single interaction. If the photon's energy was high enough, the electron could break free from the metal surface. If the photon's energy was too low, nothing happened. This simple picture explained Leonard's observations perfectly. Bright light contains many photons, which means more electrons are ejected. But the energy of each electron depends on the energy of the individual photon, which is determined by the frequency of the light. This also explained the threshold frequency. Below a certain frequency, photons simply did not carry enough energy to release electrons from the metal. Einstein's theory provided a clean and elegant solution, yet it was deeply unsettling. For more than half a century, physicists had believed they understood the nature of light. The wave theory had explained interference, diffraction, and polarization with remarkable precision. Now Einstein was suggesting that light sometimes behaves as if it were composed of particles. Many scientists initially resisted this idea. Even Max Planck himself was cautious. Although Planck had introduced the concept of energy quanta, he was reluctant to accept that light itself might consist of discrete packets. The wave theory of light had been so successful that abandoning it seemed almost unthinkable, but experiments continued to support Einstein's interpretation. Over time, increasingly precise measurements confirmed that the energy of photoelectrons depended directly on the frequency of the incoming light, exactly as Einstein had predicted. In 1921, Einstein received the Nobel Prize in Physics, not for his famous theory of relativity, but specifically for his explanation of the photoelectric effect. The recognition reflected how important this discovery had become. Light, it seemed, could behave as both a wave and a particle. Sometimes it spread smoothly through space as a continuous electromagnetic wave. Other times it interacted with matter as individual localized quanta. This strange dual nature hinted at something deeper about the structure of reality. Radiation might not be a continuous flow of energy after all. Instead, it might consist of countless microscopic interactions occurring one discrete event at a time. In other words, nature might be built from tiny individual exchanges rather than smooth, uninterrupted processes. If that were true for light, an intriguing question naturally followed. Perhaps matter itself shared a similar dual character. perhaps the tiny particles that make up atoms might also behave like waves under the right circumstances. And as physicists soon discovered, that possibility was not merely a philosophical curiosity. It was the beginning of another profound shift in our understanding of the microscopic world. Once physicists began accepting that light could behave as both a wave and a particle, an intriguing question began to circulate quietly through the scientific community. If radiation could sometimes behave like matter, might matter sometimes behave like radiation? In other words, could the tiny particles that make up the physical world also possess wave-like properties? This idea might sound unusual at first, but it emerged naturally from the new quantum thinking that was beginning to take shape in the early 20th century. The scientist who proposed this bold possibility was a young French physicist named Louis de Broglie. De Broglie came from an aristocratic family in France and initially studied history before turning toward physics. By the early 1920s, he had become fascinated by the strange dual nature of light that had been revealed through the work of Max Planck and Albert Einstein. Light, according to these discoveries, behaved both as a continuous electromagnetic wave and as discrete packets of energy called photons. De Broglie wondered whether this duality might extend further. Perhaps the symmetry worked both ways. If waves could sometimes act like particles, perhaps particles could also act like waves. In 1924, de Broglie presented this idea in his doctoral thesis at the University of Paris. His proposal was surprisingly simple, yet deeply radical. He suggested that every particle with momentum should be associated with a wave. The relationship between the particle and its wave could be expressed through a remarkably compact idea. In words, his hypothesis stated that the wavelength associated with a particle equals Planck's constant divided by the particle's momentum. Momentum in this context means the product of a particle's mass and its velocity. Larger objects moving slowly have large momentum, while extremely small particles moving quickly can have comparable values. Planck's constant, which had already appeared in earlier quantum work, is extraordinarily small. Its value is approximately 6.626 times 10 to the minus 34 joule-seconds. Because this number is so tiny, the wavelength associated with ordinary objects is unimaginably small. For example, consider a baseball weighing roughly 140 grams travelling at about 40 meters per second. If one calculates the wavelength associated with that baseball using de Broglie's formula, the result is so incredibly small that it becomes completely undetectable. In practical terms, everyday objects never display noticeable wave behaviour, but electrons, atoms, and other microscopic particles are vastly lighter. Their momentum can be small enough for the associated wavelength to become measurable. This meant that, under the right conditions, particles might produce the same kinds of interference and diffraction patterns that had previously been observed only with waves. At first, de Broglie's idea was purely theoretical. No one had yet observed such behaviour directly. Yet the proposal impressed some of the leading scientists of the time. Among them was Albert Einstein, who immediately recognized the elegance and potential importance of the hypothesis. Einstein supported de Broglie's work enthusiastically, helping to bring attention to the young physicist's thesis. But physics is ultimately an experimental science. The real question was whether matter waves could actually be observed in the laboratory. A few years later, the answer arrived in a rather unexpected way. In the United States, two researchers working at Bell Telephone Laboratories were conducting experiments on electron scattering. Their names were Clinton Davison and Lester Germer. Davison and Germer were studying how beams of electrons bounced off metal surfaces, particularly a crystal made of nickel. Their apparatus fired a narrow stream of electrons toward the crystal, and then measured how those electrons scattered after striking the surface. Initially, their goal was not to test de Broglie's hypothesis. They were simply investigating the behaviour of electrons interacting with solid materials. But during the course of their work, an accident occurred that unexpectedly improved the quality of their nickel crystal. The crystal structure became more orderly, creating a surface that behaved like a well-aligned lattice of atoms. When the researchers directed electrons toward this crystal, something remarkable happened. Instead of scattering randomly, the electrons produced a pattern of peaks and troughs in their intensity. The pattern closely resembled the diffraction patterns produced when waves pass through a regularly spaced structure. In other words, the electrons were behaving exactly like waves. The crystal lattice acted like a diffraction grating, causing the electron waves to interfere constructively at certain angles and destructively at others. The observed angles of these diffraction peaks matched precisely the wavelengths predicted by de Broglie's equation. This experiment provided direct evidence that particles of matter could display wave properties. Almost simultaneously, another scientist working in England reached a similar conclusion through an entirely independent approach. His name was George Paget Thomson, the son of J.J. Thomson, the physicist who had originally discovered the electron in 1897. The irony of this story is rather charming. J.J. Thomson had shown that electrons were particles. Now his own son was helping demonstrate that those same electrons behaved like waves. George Paget Thomson performed experiments in which electrons were accelerated through thin metal films. As the electrons passed through these materials, they produced circular diffraction patterns on photographic plates. These patterns again revealed clear wave-like interference. The wavelength of the electron waves matched de Broglie's predictions with impressive accuracy. By the late 1920s, the evidence was undeniable. Electrons, which had long been treated as tiny particles orbiting atomic nuclei, also behaved like waves under the right experimental conditions. This discovery forced physicists to rethink one of the most basic categories in science. For centuries, waves and particles had been considered completely different things. Waves spread out through space and interfere with one another. Particles occupy definite positions and follow clear trajectories. But now those categories were beginning to blur. Light behaved like both a wave and a particle. Electrons behaved like both a particle and a wave. The universe, it seemed, was not interested in respecting the neat categories that human intuition preferred. Instead of choosing between waves and particles, nature appeared to combine aspects of both. One way to understand this strange duality is to imagine that what we call a particle might actually be a localized disturbance within a deeper wave-like structure. Rather than being a tiny solid object moving through space, an electron might be better described as a concentrated ripple within a broader physical field. In this view, particles are not separate from waves. They are waves, but waves that sometimes behave as if they were compact objects. This idea would soon become central to the emerging framework of quantum physics. Yet recognizing the existence of matter waves was only the beginning. Once physicists accepted that particles could behave like waves, a new challenge appeared. How could such waves be described mathematically? What kind of equations could capture the behavior of entities that seem to exist partly as particles and partly as waves? Answering that question would require a completely new kind of physics. By the middle of the 1920s, physicists had gathered a collection of intriguing clues about the microscopic world. Light sometimes behaved like particles called photons. Electrons and other particles could produce interference patterns like waves. Energy seemed to come in discrete units rather than flowing smoothly. These discoveries were fascinating, but they raised a deeper challenge. If matter and radiation behaved in these strange ways, how could scientists describe their motion mathematically? Classical physics relied on equations that tracked the exact positions and velocities of objects through time. Newton's laws allowed one to calculate a precise trajectory, much like predicting the path of a thrown stone. But the new discoveries suggested that microscopic objects did not follow such clear paths. Instead, they displayed behaviors that resembled waves spreading through space. Physicists needed a new kind of mathematics. The first breakthrough arrived through the work of a young German physicist named Werner Heisenberg. Heisenberg was deeply interested in the structure of atoms and the patterns of light emitted by excited atoms. When atoms absorb energy, their electrons can move to higher energy states. When those electrons fall back to lower states, the atom emits light at specific frequencies. Spectroscopic measurements had shown that atoms produced very precise lines in the spectrum, each corresponding to a particular transition between energy levels. Heisenberg realized that instead of trying to visualize electrons orbiting the nucleus like tiny planets, it might be better to focus only on quantities that could actually be observed. This idea led him to develop a new mathematical framework in 1925 known as matrix mechanics. The mathematics involved arrays of numbers arranged in rows and columns called matrices. These matrices represented observable quantities such as energy levels and transition frequencies. While the approach was mathematically sophisticated, the underlying philosophy was surprisingly practical. Rather than trying to imagine invisible electron orbits, Heisenberg's method described the relationships between measurable quantities directly. To help develop this theory, Heisenberg worked closely with two colleagues, Max Born and Pascal Jordan at the University of Göttingen in Germany. Born, a highly respected mathematician and physicist, recognized that Heisenberg's unusual calculations followed the rules of matrix algebra. Together with Jordan, they refined the mathematical structure and helped transform Heisenberg's ideas into a coherent theoretical framework. Pascal Jordan played a particularly important role in formalizing the algebraic relationships that governed quantum quantities. His work helped clarify how physical variables such as position and momentum behaved within the new theory. Although matrix mechanics was extremely powerful, many physicists initially found it difficult to visualize. Around the same time, another physicist working in Austria approached the problem from a very different direction. His name was Erwin Schrödinger. Schrödinger was inspired by Louis de Broglie's idea that particles possess wave-like properties. If electrons behaved like waves, perhaps their motion could be described using equations similar to those used for other wave phenomena. In 1926, Schrödinger introduced a new equation that described how these matter waves evolve through time. In spoken form, the core idea behind his equation can be summarized as follows. The change in a quantum wave through time is determined by the particle's energy, which includes both its kinetic energy and the potential energy arising from forces acting upon it. This relationship, now known as the Schrödinger equation, became one of the central equations of quantum physics. When applied to simple systems such as the hydrogen atom, the equation produced solutions that matched experimental observations remarkably well. The equation predicted that electrons in atoms could occupy only certain allowed energy levels. These energy levels corresponded exactly to the spectral lines observed in atomic emission experiments. What made this success particularly impressive was that Schrödinger's theory arrived independently of Heisenberg's matrix mechanics. At first, the two approaches appeared completely different. One relied on abstract matrices and algebraic relationships. The other used wave equations resembling those of classical physics. But in 1926, it was shown that the two methods were mathematically equivalent. They were simply different ways of describing the same underlying physical reality. This unification gave physicists confidence that they had discovered the correct mathematical framework for the microscopic world. Yet one crucial question remained. What exactly did the wave described by the Schrödinger equation represent? Did it correspond to a physical wave moving through space, similar to a ripple on water, or did it represent something more abstract? The answer was proposed by Max Born, the same physicist who had helped develop Heisenberg's matrix mechanics. Born suggested that the wave described by the Schrödinger equation should not be interpreted as a physical wave of matter. Instead, it represented a probability wave. In other words, the wave function described the likelihood of finding a particle at different locations. According to Born's interpretation, the height of the wave at a particular point corresponds to the probability of detecting the particle there. If the wave is strong in one region, the particle is more likely to be found there during a measurement. If the wave is weak, the probability of finding the particle in that region is lower. This idea introduced a profound shift in the philosophy of physics. Classical physics had always aimed to predict the exact behavior of objects. Given enough information about the initial conditions, one could calculate the precise motion of planets, projectiles, or pendulums. Quantum mechanics offered something different. Instead of predicting definite outcomes, it predicted probabilities. For example, if one prepares an electron in a particular quantum state, the theory does not say exactly where the electron will be detected. Instead, it provides a probability distribution describing where the electron is most likely to appear. When an experiment is repeated many times under identical conditions, the results follow this probability pattern with remarkable precision. This shift from certainty to probability was unsettling for many physicists. Even Albert Einstein, who had contributed so much to the early development of quantum theory, expressed deep discomfort with the idea. Einstein famously remarked that he did not believe that nature fundamentally relied on chance. His sentiment is often summarized by the phrase that God does not play dice with the universe. Yet experimental evidence continued to confirm the predictions of quantum mechanics. Despite its unusual interpretation, the mathematics worked extraordinarily well. The Schrödinger equation accurately described the energy levels of atoms, the behavior of electrons in molecules, and the interactions between radiation and matter. Quantum mechanics eventually became the foundation for entire fields of science, including quantum chemistry, solid-state physics, and nuclear physics. The technology of the modern world depends heavily on these principles. Semiconductor devices, lasers, magnetic resonance imaging, and countless other technologies rely on calculations derived from quantum mechanics. What makes this situation especially fascinating is the contrast between the theory's predictive power and its conceptual strangeness. The equations of quantum mechanics allow physicists to calculate experimental outcomes with extraordinary accuracy. In some cases, theoretical predictions agree with measurements to more than 10 decimal places, and yet the underlying meaning of those equations remains deeply mysterious. The mathematics of the quantum world works beautifully. Understanding what it truly says about reality is a challenge that continues to inspire physicists to this very day. By the late 1920s, the emerging framework of quantum mechanics had already begun to reshape the way physicists thought about nature. Particles could behave like waves, energy appeared in discrete packets, and the equations describing microscopic systems predicted probabilities rather than precise outcomes. Yet another startling realization was still waiting just around the corner. This realization would reveal that the very act of measuring certain properties of a particle carries unavoidable limitations. The scientist who uncovered this principle was Werner Heisenberg, the same physicist who had helped create the mathematical foundations of quantum mechanics. In 1927, Heisenberg introduced what is now known as the uncertainty principle. The central idea is surprisingly simple to state, although its implications are profound. Heisenberg discovered that certain pairs of physical quantities cannot both be known with unlimited precision at the same time. The most famous example involves position and momentum. Position tells us where a particle is located in space. Momentum tells us how fast it is moving and in which direction. Momentum is calculated as the product of a particle's mass and its velocity. According to the uncertainty principle, the more precisely we determine a particle's position, the less precisely we can know its momentum. And conversely, the more precisely we determine its momentum, the less precisely we can know its position. This relationship can be expressed in a compact mathematical form. In clear-spoken language, the principle states that the uncertainty in position multiplied by the uncertainty in momentum must always be greater than or equal to 1/2 of Planck's constant. Planck's constant, which has already appeared in several earlier quantum ideas, is extremely small. Its value is roughly 6.626 times 10 to the minus 34 joule-seconds. Because this number is so tiny, the uncertainty principle has almost no noticeable effect in everyday life. If you throw a tennis ball across a court, you can measure its position and speed with extraordinary accuracy. The uncertainty in those measurements is far smaller than anything you could detect without highly specialized equipment, but when dealing with electrons, atoms, and other microscopic particles, the situation changes dramatically. At those scales, Planck's constant becomes large enough to matter. Attempts to measure position with extreme precision inevitably disturb the particle's momentum, and attempts to measure momentum precisely blur our knowledge of the particle's position. It is tempting to imagine that this limitation arises because our measuring devices are imperfect. However, the uncertainty principle is not simply a practical limitation. It arises directly from the mathematical structure of quantum mechanics itself. The wave functions that describe particles cannot simultaneously produce infinitely sharp values for both position and momentum. The mathematics forbids it. The formal mathematical derivation of this principle was provided shortly after Heisenberg's original insight by a physicist named Earl Hesse Kennard. Kennard demonstrated that the uncertainty relationship follows directly from the properties of wave functions and their associated mathematical operators. In other words, the limitation is not a consequence of experimental clumsiness. It is a fundamental feature of the theory. To understand why this happens, it helps to think about the wave-like nature of particles. A particle described by a wave function behaves somewhat like a wave packet. This packet represents a spread of possible positions. If we try to compress the wave packet so that the particle's position becomes extremely well defined, the wave must contain many different wavelengths. Each wavelength corresponds to a different momentum. As a result, the particle's momentum becomes uncertain. On the other hand, if we construct a wave with a very precise wavelength, corresponding to a well-defined momentum, the wave must spread out across space. In that case, the particle's position becomes uncertain. This trade-off between position and momentum lies at the heart of the uncertainty principle. One of the most important consequences of this idea concerns the structure of atoms. In classical physics, electrons orbiting the nucleus of an atom might be expected to lose energy through radiation and gradually spiral inward until they collapse into the nucleus. Such a collapse would make stable atoms impossible, yet atoms clearly exist, and they remain stable over enormous spans of time. Quantum uncertainty plays a crucial role in preventing this collapse. If an electron was squeezed into an extremely small region, directly inside the nucleus, its position would become very precisely defined. According to the uncertainty principle, this would create enormous uncertainty in the electron's momentum. That uncertainty corresponds to extremely high kinetic energy. In simple terms, confining the electron too tightly would cause it to gain so much energy that it would be forced outward again. This effect helps maintain the stable structure of atoms. The electron remains spread out in a cloud-like probability distribution surrounding the nucleus, rather than collapsing inward. The uncertainty principle therefore contributes directly to the stability of matter itself. Without it, atoms would behave very differently, and the familiar chemistry of the world might not exist. Beyond atomic physics, the uncertainty principle also forces us to reconsider one of the most deeply rooted ideas in classical science. In Newtonian mechanics, it was assumed that every object follows a precise trajectory through space and time. If one knows the exact position and velocity of an object at a particular moment, one can calculate its entire future motion. This idea is sometimes called determinism. Quantum mechanics challenges that assumption. If position and momentum cannot both be known with unlimited precision, then the idea of a perfectly defined trajectory begins to lose its meaning. Instead of a single path through space, a quantum particle is described by a spread of possibilities. The wave function encodes these possibilities, and measurements reveal one particular outcome among many potential alternatives. This shift represents more than just a technical detail in physics. It introduces the possibility that uncertainty is woven into the fabric of nature itself. The limits described by Heisenberg's principle may not simply reflect our lack of knowledge. They may represent genuine boundaries on what can be known about the universe. For some scientists, this idea was deeply unsettling. Albert Einstein, for example, believed that the apparent randomness of quantum mechanics must arise from some deeper level of hidden physical laws. Others embraced the new perspective, viewing uncertainty as an essential ingredient of the microscopic world. Regardless of one's philosophical preferences, the experimental evidence has repeatedly confirmed the predictions of quantum mechanics. The uncertainty principle is not merely a theoretical curiosity. It has been verified in countless experiments and lies at the heart of modern technologies ranging from electron microscopes to quantum computing research. In the quiet mathematics of quantum theory, uncertainty is not a flaw, it is a feature. And through that feature, the universe reveals a subtle but profound truth. The act of observing nature is not always separate from the behavior of nature itself. One of the most revealing experiments in all of physics involves a piece of equipment that is almost disarmingly simple: a light source, a barrier with two narrow openings, and a screen placed behind the barrier. Despite this simplicity, the experiment reveals something deeply strange about the nature of reality. The story begins in the early 1800s with an English physician and scientist named Thomas Young. Young was fascinated by the behavior of light and wanted to understand whether it behaved like a stream of tiny particles or like a wave spreading through space. At the time, this question was still under active debate. To investigate the matter, Young performed what would later become known as the double-slit experiment. He directed a beam of light toward a barrier containing two extremely narrow slits. Behind the barrier, he placed a screen where the light could be observed. If light consisted of particles travelling in straight lines, the expectation was straightforward. Each slit would allow a small beam of light to pass through, producing two bright bands on the screen. But that is not what Young observed. Instead of two simple bands, the screen displayed a pattern of alternating bright and dark stripes. This pattern was an example of interference, a phenomenon that occurs when waves overlap. When two waves combine, their peaks can reinforce one another, producing bright regions. In other places, a peak from one wave may meet a trough from another, cancelling each other out and producing darkness. The pattern Young observed matched exactly what one would expect if light were behaving as a wave. This experiment played a major role in convincing scientists that light was not made of particles after all, but rather consisted of waves travelling through space. For many decades, the wave theory of light seemed firmly established. However, the development of quantum physics brought new questions. If light could also behave as particles called photons, what would happen if the double-slit experiment were performed with extremely faint light? Suppose one arranged things so carefully that only a single photon passed through the apparatus at any given moment. Classically, a photon travelling as a particle should pass through one slit or the other. If that were the case, each photon would strike the screen in a location corresponding to the slit it passed through. Over time, the pattern would build up into two broad clusters. But experiments showed something very different. When physicists reduced the light intensity so that photons travelled through the apparatus one at a time, each photon did indeed appear on the screen as an individual dot. Yet as more and more photons accumulated, the familiar interference pattern gradually emerged. Bright bands formed in some regions. Dark bands appeared in others. The astonishing conclusion was that each individual photon somehow contributed to the wave interference pattern. It was as though each photon passed through both slits simultaneously and interfered with itself. This result was puzzling enough when dealing with light, but the mystery deepened when scientists began performing the same experiment with particles of matter. In the 1920s and 1930s, researchers confirmed that electrons, which had previously been considered tiny particles, could also produce interference patterns. In modern laboratories, physicists have taken this idea even further. Sophisticated instruments allow researchers to fire electrons through a double-slit apparatus one at a time, carefully controlling the timing so that each electron travels through the system alone. Once again, the results are astonishing. Each electron strikes the detector as a single localized point, but when many such events accumulate, the pattern that forms on the screen is unmistakably an interference pattern. The electrons behave as though each one travels through both slits simultaneously, producing overlapping waves that interfere. This effect is not limited to electrons. Experiments have demonstrated interference patterns for neutrons, atoms, and even complex molecules. One remarkable set of experiments has been conducted by research groups at the University of Vienna, where physicists have studied interference involving molecules composed of dozens or even hundreds of atoms. These molecules are far larger than the particles originally studied in early quantum experiments. Yet under carefully controlled conditions, they too display wave-like interference. This raises an unsettling question. If particles behave like waves when passing through two slits, what happens if we try to determine which slit the particle actually travels through? Physicists have designed experiments to answer exactly that. Sensitive detectors can be placed near the slits in order to observe which path the particle takes. When such detectors are active, the interference pattern disappears. Instead of a series of bright and dark stripes, the pattern on the screen becomes two broad bands, exactly what one would expect if particles travelled through one slit or the other. In other words, the act of observing the particle's path appears to change the outcome of the experiment. Without observation, the particle behaves like a wave passing through both slits. With observation, the particle behaves like a localized object travelling through a single slit. This result has fascinated and puzzled physicists for nearly a century. It suggests that the act of measurement plays a crucial role in determining how quantum systems behave. Different interpretations of quantum mechanics offer different explanations for this phenomenon. Some suggest that measurement causes the wave function to collapse into a single outcome. Others propose that the particle's behavior always involves multiple possibilities that only appear definite once a measurement occurs. Regardless of interpretation, the experimental facts remain clear. The double-slit experiment demonstrates that particles at the quantum scale do not behave like tiny billiard balls travelling along definite paths. Instead, they exhibit a blend of wave-like and particle-like behaviour that defies simple classical descriptions. Even Richard Feynman, one of the most influential physicists of the 20th century, remarked that the double-slit experiment contains the central mystery of quantum mechanics. If one truly understands what this experiment reveals, one has grasped the essence of quantum theory. It is a humble apparatus consisting of two narrow slits, yet it reveals something profound about the nature of the universe. Reality at the smallest scales does not conform to our everyday expectations. Instead, it behaves in ways that continue to challenge intuition and inspire deeper questions about the fundamental structure of the world. When physicists began exploring the strange behavior revealed by quantum experiments, they discovered that the mathematics describing microscopic systems had a remarkable feature. This feature is known as quantum superposition. To understand the idea, it helps to begin with something familiar. In classical physics, an object is always assumed to occupy a single definite state. A coin lying on a table is either heads or tails. A planet orbiting a star has a single position and velocity at any moment. A switch is either on or off. Classical reasoning assumes that nature always chooses one specific outcome. Quantum theory introduces a very different picture. According to the mathematics of quantum mechanics, a physical system can exist in a combination of multiple possible states at the same time. This combination is called a superposition. Rather than occupying a single definite condition, the system is described by a collection of possibilities that coexist simultaneously. Only when a measurement takes place does one particular outcome appear. This idea is deeply connected to the wave-like description of particles introduced earlier through the Schrödinger equation. The wave function associated with a quantum system contains information about all the possible outcomes that might be observed. Each possibility contributes to the overall wave, and the different components can overlap with one another in ways that resemble the interference of ordinary waves. One of the scientists who helped clarify the mathematical structure behind these ideas was the British physicist Paul Dirac. Dirac was known for his extraordinary ability to express complicated physical concepts through elegant mathematical language. In the late 1920s, he developed a powerful formalism that allowed physicists to describe quantum states using abstract mathematical objects known as vectors. Within this framework, quantum states could be added together to form new states. This property, called linear superposition, lies at the heart of quantum mechanics. If one possible state of a system is represented mathematically, and another possible state is also represented, then a weighted combination of those states is itself a valid quantum state. The wave function describing the system can therefore contain multiple overlapping components. Each component corresponds to a possible outcome that might be observed during a measurement. The mathematics does not insist that the system must choose one possibility immediately. Instead, the different possibilities coexist within the quantum description. When a measurement is performed, the wave function produces a specific result according to the probabilities encoded within it. This interpretation is closely connected to the probability interpretation introduced by Max Born. Born proposed that the wave function should not be interpreted as a physical wave of matter. Instead, it represents a probability amplitude. In simpler terms, the wave function contains information about how likely different outcomes are. Regions where the wave function has greater magnitude correspond to outcomes that are more likely to occur during an observation. Regions where the wave function is small correspond to less likely outcomes. Before a measurement occurs, the system is described by the full combination of possibilities contained in the wave function. After a measurement, one outcome appears. The mathematics provides the probabilities, but it does not determine exactly which outcome will occur in any single event. This idea challenges one of the most deeply rooted assumptions of classical physics. In the classical picture, the world is thought to exist in a single objective state at every moment. Even if we do not know all the details, we assume that the system itself has definite properties waiting to be discovered. Quantum superposition suggests something more subtle. Before measurement, a system may not possess a single definite value for certain properties. Instead, the system is described by a spread of possibilities that coexist within the wave function. Only when an observation takes place does the system appear to adopt a definite state. This strange situation has led physicists to reconsider what it means to describe reality. Some interpretations suggest that quantum states represent objective physical conditions. Other interpretations propose that the wave function reflects our knowledge about the system rather than the system itself. These philosophical debates remain active today. Regardless of interpretation, the mathematical predictions of quantum mechanics have been confirmed by countless experiments. Superposition is not merely an abstract idea, it produces real and measurable effects. One important example appears in modern efforts to build quantum computers. Traditional computers store information in units called bits. Each bit can take one of two values, often represented as 0 or 1. Quantum computers use a different type of information unit known as a quantum bit, or qubit. Unlike classical bits, qubits can exist in a superposition of states corresponding to 0 and 1 simultaneously. This property allows quantum computers to perform certain calculations in ways that are fundamentally different from classical machines. Researchers at institutions such as the Massachusetts Institute of Technology, the University of Oxford, and IBM Quantum have been developing experimental quantum processors that exploit superposition to perform specialized computational tasks. Although practical large-scale quantum computers remain a major engineering challenge, early prototypes have already demonstrated the power of quantum superposition in controlled laboratory environments. The same principle that once puzzled early physicists is now becoming a resource for new technologies. Yet the idea of superposition also leads naturally to a deeper puzzle. If quantum systems can exist in combinations of possibilities, why do we not observe such mixtures in the everyday world? Why do objects around us appear to occupy definite states rather than multiple possibilities at once? This question touches on one of the central mysteries of quantum mechanics. Somewhere between the microscopic world of atoms and the familiar scale of human experience, the overlapping possibilities described by quantum theory seem to resolve into the single outcomes we observe. Understanding how and why this transition occurs remains one of the most fascinating challenges in modern physics. The concept of superposition therefore opens the door to a deeper exploration of measurement, observation, and the nature of reality itself. And as physicists continued investigating these questions, they soon encountered a thought experiment that would become one of the most famous puzzles in the entire history of science. As quantum mechanics developed during the early decades of the 20th century, physicists gradually became comfortable using its equations to predict experimental results. The mathematics worked beautifully. Wave functions evolved smoothly according to the Schrödinger equation, and probabilities calculated from those wave functions matched measurements with astonishing precision. Yet behind this success lurked a conceptual puzzle that continues to provoke debate even today. This puzzle is known as the measurement problem. To appreciate the difficulty, it helps to recall the idea of quantum superposition. According to the equations of quantum mechanics, a system can exist in a combination of multiple possible states simultaneously. The wave function describing the system includes all these possibilities at once. But when an experimenter performs a measurement, the result is always a single definite outcome. The mathematical description suddenly appears to reduce from many possibilities to just one. The question that troubled physicists was simple to state but difficult to answer. What exactly happens during measurement? Does the wave function physically change in some way? Or does measurement merely reveal information that was already present but hidden? One of the most famous illustrations of this puzzle was proposed by the Austrian physicist Erwin Schrödinger in 1935. Schrödinger was one of the architects of quantum mechanics and understood its mathematics extremely well. Yet he was uneasy about the implications of superposition when applied to everyday objects. To highlight the difficulty, he proposed a deliberately strange thought experiment that has since become legendary. Imagine a sealed box containing a living cat. Inside the box there is also a small radioactive atom. Radioactive atoms are unstable and decay randomly over time. In a given interval there might be a certain probability that the atom will decay, and a certain probability that it will remain intact. Connected to the atom is a detection device. If the atom decays, the detector triggers a small mechanism that releases a vial of poison gas inside the box. If the atom does not decay, the poison remains sealed and the cat remains unharmed. Now consider what quantum mechanics says about the atom. Before observation, the atom can be described as existing in a superposition of two possibilities, decayed and not decayed. Because the fate of the cat is linked to the state of the atom, the entire system becomes entangled with that quantum uncertainty. According to a strict reading of the mathematics, the cat itself would then exist in a superposition of two states, alive and dead at the same time. Schrödinger never intended this scenario to be taken literally. His goal was to illustrate how strange the implications of quantum theory become when applied to objects large enough to see. In everyday experience, cats are quite firmly in one condition or the other. Fortunately for the cats of the world, we do not encounter situations where they are simultaneously alive and dead. Schrödinger's thought experiment therefore raised a crucial question. At what point does a quantum superposition become a single definite outcome? Is there a special boundary between the microscopic quantum world and the macroscopic world we experience? Or does the mathematics apply at every scale? Physicists quickly realized that the process of measurement involves more than just the system being observed. It also includes the measuring device itself. This idea was analysed in detail by the Hungarian-American mathematician and physicist John von Neumann. In his 1932 book Mathematical Foundations of Quantum Mechanics, von Neumann studied how quantum systems interact with measuring instruments. He pointed out that the measuring device must also obey the laws of quantum mechanics. If the measured system becomes entangled with the measuring apparatus, then the apparatus itself can enter a superposition of states corresponding to different measurement outcomes. For example, a detector might exist in a superposition of registering a particle and not registering it. But if that detector is observed by another device, the second device also becomes entangled with the system. Von Neumann described this situation as a measurement chain. The chain could extend from the microscopic particle to the detector, from the detector to a recording instrument, from the instrument to a scientist reading the result, and possibly even further. Each step in the chain could, in principle, become part of a larger quantum superposition. This reasoning led von Neumann to a provocative question. If every physical system obeys quantum mechanics, where exactly does the chain stop? At what point does the superposition collapse into a single observed outcome? Some early interpretations suggested that conscious observation might play a special role in this process. According to this view, the wave function collapses when a conscious observer becomes aware of the result. This idea attracted attention in the early days of quantum theory, although most modern physicists approach it with caution. Other interpretations propose that wave function collapse is a genuine physical process that occurs when a quantum system interacts with its environment. Still others argue that the wave function never collapses at all, and that all possible outcomes continue to exist simultaneously in different branches of reality. Regardless of interpretation, the measurement problem highlights a deep tension within quantum mechanics. On one hand, the Schrödinger equation describes the smooth evolution of wave functions over time. On the other hand, measurements appear to produce sudden and definite outcomes. The transition between these two descriptions remains one of the most intriguing conceptual questions in modern physics. Physicists have developed many experimental techniques to explore these issues, including delicate experiments involving trapped ions, superconducting circuits, and ultra-cold atoms. Research groups at institutions such as the National Institute of Standards and Technology, the University of Innsbruck, and Yale University have performed experiments that probe the boundary between quantum superpositions and classical behavior. These studies suggest that interactions with the surrounding environment tend to destroy delicate quantum superpositions, a process known as decoherence. Decoherence does not completely solve the measurement problem, but it helps explain why large objects rarely display obvious quantum behavior. As systems grow larger and interact with more particles in their surroundings, their quantum states become entangled with countless environmental degrees of freedom. The delicate interference patterns associated with superposition quickly fade. Yet even with this understanding, the deeper philosophical questions remain open. What exactly is the wave function? Does it represent a physical object, a state of knowledge, or something else entirely? And how do definite outcomes arise from a theory that describes overlapping possibilities? These questions continue to inspire new interpretations and new experiments. They also lead naturally toward another remarkable phenomenon that lies at the heart of quantum mechanics, a phenomenon in which two particles can become linked so deeply that the state of one instantly influences the state of the other, even across enormous distances. This phenomenon is known as quantum entanglement, and its discovery would reveal just how interconnected the quantum world can be. Among the many strange ideas that emerge from quantum mechanics, one stands out as particularly surprising. It suggests that two particles can become linked in such a deep and fundamental way that their properties remain correlated even when the particles are separated by large distances. This phenomenon is known as quantum entanglement. To understand the idea, imagine two particles that interact with one another in a specific way. During their interaction, certain properties of the pair become connected. For example, suppose the particles are created together with a property known as spin, a form of intrinsic angular momentum carried by many quantum particles. In a simple entangled state, the total spin of the pair might be fixed so that one particle must have spin pointing in one direction, while the other has spin pointing in the opposite direction. Before measurement, the quantum state of the pair contains both possibilities at once. Neither particle individually possesses a definite spin direction. Instead, the pair is described by a shared wave function that encodes the relationship between them. When an experimenter measures the spin of one particle, the result instantly determines the spin of the other. If the first particle is found to have spin pointing upward, the second must have spin pointing downward. If the first is downward, the second must be upward. What makes this effect remarkable is that the particles can be separated by great distances before the measurements occur. Even if they are many kilometers apart, the measurement outcomes remain perfectly correlated. This phenomenon was first examined carefully in a famous paper published in 1935 by Albert Einstein, Boris Podolsky, and Nathan Rosen. The paper is now commonly known as the EPR paper, named after the initials of its authors. Einstein and his colleagues were deeply uneasy about the implications of quantum mechanics. They believed that the theory might be incomplete, missing some deeper set of underlying variables that would restore determinism and locality. Locality is an important principle in physics. It states that objects can only influence one another through interactions that travel through space at finite speeds. In Einstein's theory of relativity, no signal can travel faster than the speed of light, which is approximately 300,000 kilometers per second. The EPR paper argued that if quantum mechanics were correct, then measuring one particle could instantly influence the state of another distant particle. Einstein famously described this possibility as spooky action at a distance. Einstein found this idea deeply troubling because it seemed to violate the principle that information cannot travel faster than light. To resolve the puzzle, Einstein suggested that quantum mechanics might be missing some hidden variables. These hidden variables would determine the outcomes of measurements in advance, restoring a classical picture of reality. For many years, the debate remained largely philosophical. Then, in the 1960s, a physicist from Northern Ireland named John Bell discovered a remarkable result. Bell showed that the predictions of quantum mechanics differ in a measurable way from any theory that relies on local hidden variables. He derived a set of mathematical relationships, now known as Bell's inequalities, that place limits on the correlations that can occur in any theory based on local hidden variables. In clear terms, Bell demonstrated that if the world obeys local hidden variable rules, certain statistical correlations between measurement outcomes must remain within specific bounds. Quantum mechanics predicted that those bounds could be exceeded. This insight transformed the debate from a philosophical discussion into an experimental question. If physicists could measure the correlations between entangled particles with sufficient precision, they could determine whether nature followed Bell's inequalities or violated them. The first convincing experimental tests were performed in the early 1980s by the French physicist Alain Aspect and his colleagues. Aspect's team used pairs of entangled photons produced through a process known as atomic cascade emission. These photons were sent toward detectors positioned at different orientations. By rapidly changing the measurement settings during the flight of the photons, the researchers ensured that the measurement choices could not influence one another through ordinary signals traveling at the speed of light. When the results were analyzed, the correlations between the photons clearly violated Bell's inequalities. The experimental data agreed with the predictions of quantum mechanics and disagreed with the expectations of local hidden variable theories. In the decades that followed, many additional experiments confirmed these results with increasing precision. Research groups around the world refined the techniques, closing potential experimental loopholes and strengthening the conclusions. One of the leading figures in this field has been the Austrian physicist Anton Zeilinger. Zeilinger and his collaborators conducted numerous experiments demonstrating entanglement over increasingly large distances. In some cases, entangled photons were transmitted through optical fibers spanning several kilometers. In other experiments, photons were sent between ground stations and satellites. These studies confirmed that quantum entanglement remains intact even when particles are separated by vast distances. Despite its strange appearance, entanglement does not allow faster-than-light communication in the usual sense. Although the measurement outcomes are correlated, the results themselves appear random when viewed individually. No usable signal can be transmitted faster than light using entanglement alone. Nevertheless, the phenomenon reveals that quantum systems can exhibit correlations that cannot be explained by classical local theories. The properties of entangled particles are deeply connected, regardless of the physical distance between them. Today, this once puzzling feature of quantum theory has become a powerful technological resource. Entanglement plays a central role in quantum communication. In quantum key distribution, for example, entangled photons can be used to create encryption keys that are guaranteed to be secure by the laws of physics themselves. Any attempt to intercept or measure the quantum signals would disturb the system in a detectable way. Research groups and companies around the world are currently developing quantum communication networks based on these principles. Experiments in China, Europe, and North America have already demonstrated satellite-based quantum key distribution over thousands of kilometers. Entanglement also lies at the heart of many proposals for quantum computing, where correlations between qubits allow certain calculations to be performed far more efficiently than with classical computers. What began as a philosophical puzzle about the completeness of quantum theory has therefore become one of the most important resources in modern physics. Yet the deeper meaning of entanglement continues to provoke reflection. The phenomenon suggests that the properties of quantum systems cannot always be understood by examining individual particles in isolation. Instead, the relationships between particles may carry essential information about the physical state of the system. In the quantum world, connections can matter just as much as the objects being connected. And as physicists continued exploring these ideas, they found themselves confronting an even broader set of questions about how quantum mechanics should be interpreted and what it ultimately reveals about the nature of reality itself. By the middle of the 20th century, quantum mechanics had become one of the most successful theories ever developed in science. Its equations described atomic spectra, chemical bonding, semiconductor behavior, nuclear reactions, and the interaction between matter and radiation with astonishing accuracy. Physicists could calculate experimental outcomes with precision that often extended to 10 decimal places or more. Yet despite this extraordinary success, there remained a lingering question. What exactly does the theory say about reality? The equations of quantum mechanics work beautifully, but interpreting their meaning has proven far more challenging. Over the years, physicists and philosophers have proposed several different ways of understanding the theory. These explanations are known as interpretations of quantum mechanics. Importantly, these interpretations do not change the mathematical predictions of the theory. They all reproduce the same experimental results. The differences lie in how each interpretation explains what the mathematics represents. One of the earliest and most widely discussed interpretations is known as the Copenhagen interpretation. This perspective was developed primarily by the Danish physicist Niels Bohr and the German physicist Werner Heisenberg during the 1920s. The Copenhagen interpretation emphasizes the central role of measurement in quantum theory. According to this view, physical systems are described by wave functions that represent probabilities. Before a measurement occurs, a system may exist in a superposition of several possible states. When a measurement is performed, the wave function appears to collapse, producing a single definite outcome. In this interpretation, the wave function does not necessarily represent a physical object moving through space. Instead, it represents our knowledge about the system and the probabilities of different measurement results. Bohr also introduced the concept of complementarity, which states that certain properties of quantum systems cannot be fully observed at the same time. For example, experiments may reveal either wave-like behavior or particle-like behavior, depending on how the measurement is performed. Both descriptions are necessary, but they cannot be applied simultaneously in a single experiment. The Copenhagen interpretation became widely accepted among early quantum physicists, partly because it allowed researchers to use the theory effectively without demanding a deeper explanation of its underlying reality. However, not everyone was satisfied with this approach. Some scientists felt that the Copenhagen view avoided the deeper question of what actually exists in the physical world. One alternative proposal emerged in 1957 from an American physicist named Hugh Everett III. Everett introduced what is now called the many worlds interpretation. In this interpretation, the wave function never collapses. Instead, every possible outcome described by the wave function actually occurs. When a quantum measurement takes place, the universe effectively branches into multiple versions, each corresponding to a different possible result. In one branch, a particle might be detected in one location. In another branch, it might appear somewhere else. Observers in each branch experience only one outcome, but the overall wave function continues to evolve smoothly according to the Schrödinger equation. The many worlds interpretation removes the need for a special collapse process. The mathematics of quantum mechanics remains unchanged, but the price is a universe that continually divides into many parallel histories. Although the idea initially seemed extravagant, it has gained increasing attention in modern discussions of quantum theory. Another perspective known as relational quantum mechanics was proposed by the Italian physicist Carlo Rovelli in the 1990s. Rovelli's interpretation suggests that the properties of physical systems do not exist independently in an absolute sense. Instead, properties only exist relative to other systems that interact with them. In this view, when one system measures another, a definite outcome occurs relative to that interaction. However, a different observer who has not yet interacted with the system may still describe it using a superposition of possibilities. Relational quantum mechanics therefore treats physical properties as relationships rather than absolute attributes. This interpretation reflects a broader philosophical idea that information about the world is always defined through interactions between systems. A very different approach has emerged from the field of quantum information theory. This interpretation is known as QBism, short for quantum Bayesianism. QBism has been developed and promoted by physicists such as Christopher Fuchs and his collaborators. In QBism, the wave function is interpreted as a representation of an observer's personal beliefs about the outcomes of future measurements. The probabilities calculated using quantum mechanics reflect an agent's expectations, updated through experience in a way similar to Bayesian probability theory. From this viewpoint, quantum theory is not a direct description of physical reality itself. Instead, it is a tool that allows observers to organize their expectations about how the world will respond to their actions. QBism emphasizes the role of the observer as an active participant in the process of measurement. Not all interpretations focus purely on knowledge or information. Some researchers have proposed theories in which wave function collapse is a genuine physical process occurring in nature. These ideas are known collectively as objective collapse theories. One well-known example is the Ghirardi-Rimini-Weber theory, often abbreviated as the GRW theory, developed by physicists Giancarlo Ghirardi, Alberto Rimini, and Tullio Weber in the 1980s. In the GRW model, wave functions occasionally undergo spontaneous collapses at random times. These collapses occur extremely rarely for individual particles, but become much more frequent for large systems containing many particles. As a result, microscopic systems can exist in superpositions for relatively long periods, while macroscopic objects quickly settle into definite states. This mechanism provides a possible explanation for why everyday objects do not appear to display quantum superpositions. Objective collapse models modify the equations of quantum mechanics slightly in order to include this physical collapse process. Researchers continue to investigate whether experiments might eventually detect subtle deviations predicted by these models. Despite the diversity of these interpretations, an important fact remains. All of them produce the same experimental predictions for the phenomena that have been tested so far. Whether one prefers the Copenhagen interpretation, many worlds, relational quantum mechanics, QBism, or objective collapse theories, the measurable outcomes of experiments remain identical. Quantum mechanics itself does not currently tell us which interpretation, if any, represents the ultimate nature of reality. For many physicists, this situation is both humbling and fascinating. It reminds us that a theory can be extraordinarily successful at predicting observations while still leaving open questions about what those predictions truly mean. The equations of quantum mechanics provide an incredibly precise map of the microscopic world. Understanding what that map ultimately represents remains an open journey of discovery. From its earliest days, quantum mechanics forced physicists to confront a surprising idea. At the microscopic scale, the theory seemed to describe events only in terms of probabilities. When a particle is measured, the exact outcome appears unpredictable. The equations provide probabilities for different results, but they do not specify which particular result will occur in any single experiment. For some scientists, this suggestion of genuine randomness was deeply unsettling. Classical physics had long assumed that every event had a definite cause. If one knew all the details of a system at a given moment, the future should follow inevitably from the laws of nature. This viewpoint is often called determinism. Determinism does not mean that humans can predict everything perfectly. In practice, our measurements are always limited. But the underlying assumption is that the universe itself follows precise rules that determine exactly what will happen. Quantum mechanics appeared to challenge this belief. The probabilistic nature of quantum predictions suggested that randomness might be an intrinsic feature of the universe, rather than a consequence of incomplete knowledge. Not everyone accepted that conclusion. Some physicists wondered whether the apparent randomness might simply reflect the fact that quantum theory was incomplete. Perhaps the theory was missing additional variables that determined the exact outcomes of measurements. These hypothetical quantities became known as hidden variables. If hidden variables existed, they could restore determinism by specifying the precise state of a system beneath the probabilistic surface described by quantum mechanics. The idea of hidden variables was explored in several different forms, but one of the most detailed and influential versions was developed by the American physicist David Bohm. Bohm proposed a theory now known as pilot wave theory, sometimes also called Bohmian mechanics. The roots of this idea actually stretch back to an earlier suggestion by Louis de Broglie, the physicist who first proposed that particles possess wave-like properties. During the 1920s, de Broglie briefly considered a model in which particles were guided by waves rather than being identical to them. In this picture, the wave function acts as a kind of guiding field that influences the motion of particles. Although de Broglie eventually set this idea aside, Bohm returned to it in the early 1950s and developed it into a fully consistent theory. In Bohm's framework, every particle always possesses a definite position and velocity. The motion of the particle is determined by a guiding wave described by the Schrödinger equation. This wave spreads through space and evolves according to the same mathematical rules used in standard quantum mechanics. The particle itself follows a precise trajectory, but its motion is influenced by the structure of the wave. In clear-spoken terms, Bohm's guiding rule can be summarized by saying that the velocity of a particle is determined by the gradient of the phase of the wave function that guides it. Although the details of the mathematics are intricate, the central idea is simple. Particles move along definite paths, but those paths are shaped by a guiding wave that carries information about the surrounding environment. This approach restores determinism. If one knew the exact positions of all particles and the precise form of the guiding wave, one could in principle calculate the future evolution of the system. However, Bohm's theory introduces an important feature that distinguishes it from classical physics. The guiding wave can influence particles in ways that are non-local. This means that the behavior of one particle may depend on conditions elsewhere in the system, even if the particles are widely separated. This non-local character allows Bohmian mechanics to reproduce the predictions of quantum entanglement. Although the particles follow definite trajectories, their motion can still display the correlations observed in entanglement experiments. The existence of such correlations was analysed in a very precise way by the physicist John Bell. Bell's work showed that any theory attempting to reproduce the predictions of quantum mechanics must violate at least one of two classical assumptions. Either the theory must abandon locality, meaning that distant events can influence one another instantly, or it must abandon the idea that measurement outcomes are predetermined by local hidden variables. Experiments performed over many decades have consistently supported the predictions of quantum mechanics and have shown violations of Bell's inequalities. These results rule out a wide class of hidden variable theories that preserve strict locality. However, they do not eliminate every possible deterministic model. Bohm's pilot wave theory survives because it accepts non-local connections between particles. In other words, it keeps determinism but sacrifices locality. The search for deeper explanations has continued in other directions as well. In recent years, the Dutch physicist Gerard 't Hooft, a Nobel Prize winner known for his work in particle physics, has explored the possibility that quantum mechanics might emerge from an underlying deterministic system. In some of 't Hooft's models, the fundamental dynamics of the universe operate like a complex cellular automaton. A cellular automaton is a mathematical system consisting of simple rules applied to a grid of cells. Despite the simplicity of the rules, the resulting behavior can become extremely complicated. The idea is that the apparent randomness of quantum mechanics might arise from deterministic processes occurring at a deeper level that we have not yet observed directly. These proposals remain speculative, but they illustrate the continuing interest in understanding whether quantum probabilities reflect true randomness or hidden structure. The debate touches on profound philosophical questions. Is the universe fundamentally unpredictable at its deepest level? Or does quantum theory represent a statistical description of processes governed by hidden rules? At present, no experiment has provided a definitive answer. Standard quantum mechanics continues to match experimental results with extraordinary precision. Yet the possibility that deeper theories might exist remains an open question. Physicists continue to investigate alternative frameworks, searching for clues that might reveal new layers of structure beneath the familiar equations. The exploration of hidden variables and deterministic alternatives therefore reflects a broader scientific tradition. When a theory works extremely well but raises conceptual puzzles, researchers often ask whether an even deeper theory might one day replace it. Whether such a theory exists for quantum mechanics remains uncertain, but the search itself continues to push the boundaries of our understanding of the microscopic world. As quantum mechanics matured, physicists gradually realized that the picture of individual particles moving through space was still incomplete. Electrons, photons, and other particles could be described using wave functions, but this description left an important question unresolved. What exactly is a particle? Is it truly a tiny object moving through space, or is it something more subtle? The answer that eventually emerged was both elegant and surprising. Modern physics suggests that what we call particles are not fundamental objects in their own right. Instead, they are excitations of underlying quantum fields that fill the entire universe. This idea forms the basis of quantum field theory, often abbreviated as QFT. In this framework, every type of particle corresponds to a particular field that exists everywhere in space. There is an electron field, a photon field, a quark field, and many others. These fields are not confined to specific regions. They extend throughout the universe, even in regions that appear completely empty. When a small localized vibration occurs in one of these fields, we observe it as a particle. In this sense, a particle is similar to a ripple on the surface of water. The ripple moves across the surface, but the water itself remains the underlying medium. Likewise, particles can be thought of as ripples traveling through the fabric of quantum fields. This perspective helps unify many aspects of modern physics. The interactions between particles become interactions between fields. The creation or destruction of particles corresponds to changes in the energy stored within those fields. The early development of quantum field theory was strongly influenced by the work of the British physicist Paul Dirac. Dirac was known for his remarkable ability to combine mathematical elegance with physical insight. In 1928, he developed a new equation that merged quantum mechanics with special relativity, the theory introduced by Albert Einstein that describes how space and time behave at high speeds. Dirac's equation successfully described the behavior of electrons moving at velocities close to the speed of light. In spoken form, the equation expresses the idea that the energy of a relativistic particle depends on both its momentum and its mass, combined through the structure required by Einstein's theory of spacetime. What made Dirac's work extraordinary was an unexpected prediction that emerged from the mathematics. The equation allowed solutions corresponding to electrons with negative energy. At first, this seemed puzzling, but Dirac proposed a bold interpretation. Perhaps these solutions corresponded to entirely new particles, particles identical to electrons but carrying positive electric charge. In 1932, experimental physicist Carl Anderson discovered exactly such a particle while studying cosmic rays using a cloud chamber. The new particle was called the positron, the first known example of antimatter. This discovery confirmed Dirac's prediction and provided powerful evidence that quantum field theory was revealing genuine features of the physical world. The development of quantum field theory continued through the work of many physicists in the following decades. One of the most influential contributors was the American physicist Richard Feynman. Feynman introduced an imaginative approach to quantum mechanics known as the path integral formulation. Instead of imagining a particle traveling along a single trajectory, Feynman proposed that the particle effectively explores every possible path between 2 points. Each possible path contributes to the final outcome with a certain probability amplitude. In this view, the behavior of a particle emerges from the combined contributions of all these potential histories. In spoken terms, the principle can be summarized as follows. The probability of a particle moving from one point to another is determined by adding together the contributions from every possible path the particle could take. Although this idea may sound abstract, it provides a powerful way to calculate quantum processes. Feynman also developed a visual tool that helped physicists understand interactions between particles. These visual representations are called Feynman diagrams. A Feynman diagram uses simple lines and points to represent particles and their interactions. For example, a straight line might represent an electron moving through space, while a wavy line might represent a photon. When lines meet at a point, the diagram represents an interaction between particles. These diagrams are not merely illustrations, They correspond to precise mathematical expressions that can be used to calculate the probabilities of different processes. Despite their simplicity, Feynman diagrams capture incredibly complex physical phenomena. They allow physicists to calculate how electrons scatter off one another, how particles are created in high-energy collisions, and how forces operate at the quantum level. The theoretical structure connecting these ideas was further clarified by another physicist, Freeman Dyson. Dyson demonstrated that the different approaches developed by Feynman, Julian Schwinger, and Shinichiro Tominaga were actually mathematically equivalent. Their combined work established the modern theory known as quantum electrodynamics, often abbreviated as QED. Quantum electrodynamics describes the interaction between charged particles and the electromagnetic field. It remains one of the most precise theories ever tested. Calculations based on QED predict properties of the electron with extraordinary accuracy. One famous example involves the magnetic moment of the electron, a quantity describing how the electron responds to magnetic fields. Experimental measurements and theoretical predictions for this property agree to more than 12 decimal places. Such precision represents one of the most remarkable successes in the entire history of science. Of course, theoretical predictions must ultimately be tested through experiment. One of the most important centres for such experiments is CERN, the European Organisation for Nuclear Research, located near Geneva on the border between Switzerland and France. At CERN, scientists operate the Large Hadron Collider, the most powerful particle accelerator ever built. The Large Hadron Collider is a circular machine with a circumference of about 27 kilometers. Inside this enormous ring, beams of protons are accelerated to speeds extremely close to the speed of light, and then collided head-on. The energies reached in these collisions allow physicists to probe the structure of matter at incredibly small scales. The detectors surrounding the collision points record the particles produced in these interactions, allowing researchers to compare the results with predictions derived from quantum field theory. These experiments have confirmed many aspects of the theory with remarkable accuracy. One of the most celebrated discoveries at CERN occurred in 2012, when researchers announced the observation of the Higgs boson, a particle associated with the field responsible for giving mass to many elementary particles. The discovery of the Higgs boson provided strong evidence for the framework known as the Standard Model of Particle Physics, which is built upon the principles of quantum field theory. From the quiet mathematics of Dirac's equations to the enormous machines operating deep beneath the ground at CERN, the concept of quantum fields has transformed our understanding of matter. What once seemed like a universe made of tiny solid particles now appears more like a dynamic network of fields filling space. Particles arise as ripples in those fields, appearing and disappearing as energy flows through the fabric of the cosmos. It is a picture that is both elegant and deeply surprising, and it reminds us once again that the closer we look at the structure of reality, the more subtle and fascinating it becomes. As physicists continued exploring the implications of quantum mechanics, a remarkable shift in perspective began to take shape. For centuries, science had focused on understanding matter and energy. The universe was imagined as a collection of objects interacting through forces, moving through space and time according to mathematical laws. But during the later decades of the 20th century, some researchers began asking a different kind of question. What if the deepest level of reality is not made of matter at all? What if the most fundamental ingredient of the universe is information? One of the scientists who explored this idea most passionately was the American theoretical physicist John Archibald Wheeler. Wheeler had an extraordinary career that stretched across much of the 20th century. He worked on nuclear physics during the development of the atomic bomb, helped develop the theory of black holes, and mentored generations of physicists. In his later years, Wheeler became increasingly interested in the relationship between physics and information. He summarized his view with a phrase that has since become famous, it from bit. By this, Wheeler meant that the physical world, the it, might ultimately arise from elementary units of information, the bits. In everyday computing, a bit is a simple piece of information that can take one of two values. These values are often described as 0 or 1. Wheeler proposed that the universe might operate in a similar way. Every physical event, every particle interaction, every measurement could be understood as a transformation of information. From this perspective, the properties of matter and energy might emerge from deeper informational processes. Although Wheeler's phrase was deliberately provocative, it captured a growing realization among physicists. Quantum mechanics naturally involves information. The wave function describes probabilities. Measurement outcomes reveal information about physical systems. Entanglement links the informational states of distant particles. Gradually, an entire field known as quantum information theory began to develop. One of the scientists who explored these ideas in depth is the physicist Seth Lloyd, a researcher at the Massachusetts Institute of Technology. Lloyd proposed that the universe itself might behave like a vast quantum computer. In ordinary computers, information is processed through sequences of logical operations applied to bits. These operations transform input data into output results. In a quantum computer, the basic units of information are quantum bits, or qubits. Unlike classical bits, qubits can exist in superpositions of states. This allows quantum computers to explore many possibilities simultaneously. Lloyd suggested that the fundamental interactions of particles throughout the universe might be interpreted as computational processes. Each interaction between particles could be viewed as a kind of quantum logic operation, transforming information encoded in quantum states. If this idea is correct, then the evolution of the universe itself might be understood as a continuous computation unfolding across cosmic time. In this view, stars forming, atoms interacting, and particles scattering could all be seen as steps in an enormous quantum calculation. The concept may sound abstract, but it has practical implications. Quantum information theory has provided new ways of understanding familiar quantum phenomena. Take entanglement, for example. Earlier discussions of entanglement focused on the puzzling correlations between distant particles. Quantum information theory reframes this phenomenon as a special kind of shared information. When two particles are entangled, their quantum states cannot be described independently. Instead, the information describing the system exists only in the combined state of both particles. Neither particle alone contains the full information. Only the pair together carries the complete description. This insight has led to new technologies that exploit entanglement as a resource. One of the most promising developments is quantum cryptography. Traditional encryption methods rely on mathematical complexity to protect information. With enough computing power, many classical encryption schemes could eventually be broken. Quantum cryptography uses the laws of physics themselves to guarantee security. In quantum key distribution, pairs of entangled photons are used to generate encryption keys shared between two distant parties. If an eavesdropper attempts to intercept the photons, the act of measurement disturbs the quantum state. This disturbance reveals the presence of the intruder. As a result, the communication channel can be monitored for security using the fundamental principles of quantum mechanics. Another remarkable application of quantum information is quantum teleportation. Despite the dramatic name, quantum teleportation does not involve transporting objects instantaneously through space. Instead, it allows the quantum state of one particle to be transferred to another distant particle using entanglement and classical communication. The process was first proposed theoretically in 1993 by physicists including Charles Bennett and colleagues working at the IBM Research Laboratories. In experimental demonstrations, a particle's quantum state is destroyed at one location and reconstructed at another, effectively transferring the information describing the state. Teleportation experiments have now been performed with photons, atoms, and other quantum systems. Research groups around the world, including teams in China, Europe, and North America, have demonstrated quantum teleportation across distances of hundreds and even thousands of kilometers using satellites and fiber optic networks. These achievements illustrate how the informational perspective on quantum mechanics is shaping modern technology. But the implications may extend even further. Some physicists now suspect that the structure of space-time itself may be related to patterns of quantum information. Theoretical developments in areas such as quantum gravity and black hole physics suggest that the geometry of space might emerge from the entanglement structure of underlying quantum states. For example, certain calculations in string theory and quantum gravity indicate that connections between regions of space may correspond to patterns of entanglement between quantum systems. In this view, space-time might not be a fundamental stage on which physics takes place. Instead, it could emerge from deeper informational relationships. These ideas remain under active investigation, but they highlight a striking possibility. The universe may not be built solely from particles and fields. At its deepest level, reality might be organized around the flow and transformation of information. Matter, energy, space, and time could all emerge from more fundamental informational processes. This perspective continues to inspire new research at the intersection of physics, computer science, and mathematics. And it suggests that the strange ideas first encountered in quantum mechanics may ultimately reveal something profound about the underlying structure of the cosmos itself. By the middle of the 20th century, physicists possessed two extraordinary theories that describe the universe with remarkable precision. The first was quantum mechanics, which governs the behavior of atoms, particles, and radiation at extremely small scales. The second was general relativity, developed by Albert Einstein in 1915, which explains the behavior of gravity and the large-scale structure of the universe. Each theory has been confirmed by countless experiments. Quantum mechanics accurately predicts the behavior of electrons, photons, and atomic systems. General relativity explains the motion of planets, the bending of light around massive objects, and the expansion of the universe. Yet despite their individual successes, these two theories are built upon very different foundations. Quantum mechanics describes nature in terms of probabilities, wave functions, and discrete interactions. General relativity describes gravity as the curvature of space-time, a continuous geometric structure that bends in response to mass and energy. For most situations in the universe, the two theories can be applied separately. Quantum mechanics governs the microscopic world. General relativity governs the cosmic scale. However, there are certain extreme environments where both theories should apply simultaneously. Examples include the interior of black holes and the earliest moments of the Big Bang, when the entire universe was compressed into an extremely dense state. In these situations, gravity becomes incredibly strong, while quantum effects remain essential. Physicists therefore seek a deeper theory known as quantum gravity, which would unify the principles of quantum mechanics with Einstein's description of space-time. Developing such a theory has proven to be one of the most difficult challenges in modern physics. One promising approach is known as loop quantum gravity. This theory has been developed primarily by physicists Carlo Rovelli, Lee Smolin, and their collaborators. Loop quantum gravity attempts to apply quantum principles directly to the geometry of spacetime itself. In general relativity, spacetime is treated as a smooth and continuous fabric. Loop quantum gravity proposes that spacetime may instead have a discrete structure at extremely small scales. According to this idea, the geometry of space is composed of tiny units connected in networks known as spin networks. These networks form a kind of microscopic lattice that defines the possible configurations of space. The characteristic scale at which this structure becomes important is known as the Planck length. The Planck length is roughly 1.6 times 10 to the minus 35 meters. To give a sense of how small this is, imagine dividing a single proton into 100 billion trillion pieces. Even those fragments would still be enormously larger than the Planck length. At such scales, the familiar picture of smooth space-time may break down completely. Instead, space may behave more like a discrete quantum structure made of tiny interconnected units. Another major approach to quantum gravity is known as string theory. In this framework, the fundamental building blocks of nature are not point-like particles. Instead, they are tiny one-dimensional objects called strings. These strings can vibrate in different ways, and each pattern of vibration corresponds to a different particle. For example, one vibrational pattern might represent an electron, while another might represent a photon. The idea was first explored in the 1970s and later developed extensively by many physicists. One of the most influential contributors has been the American theoretical physicist Edward Witten, whose work helped reveal deep mathematical structures within string theory. One striking feature of string theory is that it requires additional spatial dimensions beyond the familiar 3 dimensions of everyday experience. In many versions of the theory, spacetime contains 10 or even 11 dimensions. The extra dimensions are thought to be compactified, meaning they are curled up at extremely small scales and therefore invisible to ordinary observation. String theory also naturally incorporates a particle known as the graviton, which would represent the quantum carrier of the gravitational force. For this reason, string theory has long been viewed as a promising candidate for a unified theory of all fundamental interactions. Another remarkable development emerged in 1997 through the work of the Argentine physicist Juan Maldacena. Maldacena discovered a surprising relationship known as the ADS-CFT correspondence, short for anti-de Sitter conformal field theory correspondence. This duality suggests that certain theories of gravity operating within a curved spacetime can be mathematically equivalent to quantum field theories defined on the boundary of that spacetime. In other words, a theory containing gravity in one setting can correspond exactly to a theory without gravity in a lower dimensional space. This insight has provided powerful tools for studying quantum gravity and strongly interacting quantum systems. The ADS-CFT correspondence has also inspired new ideas about the relationship between spacetime and quantum information. Some researchers have proposed that the structure of spacetime itself may emerge from patterns of quantum entanglement. In this view, the connections between regions of space are determined by the entanglement relationships between underlying quantum states. If those entanglement links were altered, the geometry of spacetime might change as well. Although these ideas remain under active investigation, they hint at a profound possibility. Space and time might not be fundamental ingredients of the universe. Instead, they may arise from deeper quantum relationships among physical systems. Despite decades of effort, physicists have not yet arrived at a complete and experimentally confirmed theory of quantum gravity. Both loop quantum gravity and string theory offer promising insights, but many questions remain unanswered. Experimental tests are particularly challenging because the relevant effects are expected to occur at extremely small length scales and extremely high energies. Facilities such as the Large Hadron Collider at CERN probe energy levels far beyond those accessible in earlier experiments, but even these powerful machines remain far below the Planck scale where quantum gravity effects may become dominant. For now, the search continues. Quantum gravity remains one of the greatest unsolved problems in science, yet history suggests that such puzzles often lead to the most profound discoveries. Just as the small anomalies of blackbody radiation once led to the birth of quantum mechanics, the quest to unify gravity and quantum theory may eventually reveal an even deeper understanding of the universe. And somewhere within that deeper theory may lie new clues about the true structure of space, time, and reality itself. Even after more than a century of research, quantum mechanics continues to surprise physicists. The theory has been tested in thousands of experiments, and every careful measurement so far has confirmed its predictions. Yet the deeper implications of the theory are still being explored, and new experiments continue to push the boundaries of what quantum effects can do. One of the most fascinating directions of modern research involves testing quantum mechanics at larger and larger scales. For many years, quantum phenomena such as superposition and interference were observed only in extremely small systems, such as electrons, photons, and simple atoms. This led some scientists to wonder whether quantum effects might somehow fade away as objects grow larger. Perhaps there was a boundary between the microscopic quantum world and the macroscopic world we experience every day. To investigate this possibility, physicists began designing experiments involving increasingly complex particles. One of the pioneers in this field is the Austrian physicist Markus Arndt, who works at the University of Vienna. Arndt and his colleagues have conducted a remarkable series of experiments exploring matter-wave interference involving large molecules. In these experiments, beams of molecules are directed through extremely delicate interference apparatuses similar in spirit to the double-slit experiment. The molecules used in these studies are not simple atoms. Some of them contain dozens or even hundreds of atoms bound together in complex structures. These molecules can have masses exceeding 10,000 atomic mass units, making them vastly larger than the electrons first studied in early quantum experiments. Despite their size, these molecules still produce clear interference patterns when the experiment is carefully controlled. This means that the molecules behave as quantum waves, spreading out and interfering with themselves. The result is both beautiful and slightly unsettling. Objects that are far larger than individual atoms can still display the strange wave-like behavior predicted by quantum mechanics. The boundary between the quantum and classical worlds is therefore not determined simply by size. Instead, it depends on how strongly a system interacts with its surrounding environment. When a system interacts with many external particles, its delicate quantum superpositions tend to become scrambled through a process known as decoherence. Decoherence effectively hides quantum behavior by distributing information about the system into the surrounding environment, This process explains why everyday objects do not normally display visible interference patterns, yet when physicists carefully isolate systems from environmental disturbances, quantum effects can persist at surprisingly large scales. While experimentalists explore these fundamental questions, engineers and physicists are also working to harness quantum phenomena for practical technologies. One of the most ambitious efforts involves the creation of quantum networks. In classical communication networks, information is transmitted using electrical signals or pulses of light that carry ordinary digital data. Quantum networks aim to transmit quantum states themselves. These networks rely on entangled particles distributed between distant locations. When two nodes share entangled particles, they can perform tasks such as quantum key distribution, ensuring secure communication based on the laws of quantum mechanics. Research groups around the world are developing experimental quantum networks that link laboratories through optical fibers and satellite connections. One notable example is the MISHAS satellite, launched by Chinese researchers in 2016. This satellite has successfully transmitted entangled photons between ground stations separated by distances exceeding 1,000 kilometers. Such demonstrations show that quantum communication can operate across continental scales. Beyond communication, quantum phenomena are also driving rapid progress in several emerging technologies. Perhaps the most widely discussed is quantum computing. Unlike classical computers, which process information using bits that take definite values of 0 or 1, quantum computers use qubits that can exist in superpositions of states. When qubits become entangled with one another, they can perform certain types of calculations much more efficiently than classical machines. Research teams at organizations such as IBM Quantum, Google Quantum AI, and the University of Oxford are building experimental quantum processors containing dozens or even hundreds of qubits. Although fully scalable quantum computers remain a major engineering challenge, recent demonstrations have shown that quantum devices can outperform classical computers for certain specialized tasks. Another promising field is quantum sensing. Quantum sensors exploit delicate quantum states to measure physical quantities with extraordinary precision. For example, atomic clocks based on quantum transitions in atoms can measure time so accurately that they would lose less than 1 second over billions of years. Other quantum sensors can detect tiny variations in magnetic fields, gravitational forces, and electromagnetic radiation. These technologies have applications ranging from navigation systems to geological exploration and medical imaging. Theoretical research continues to play an equally important role in expanding the quantum frontier. Institutions such as the Perimeter Institute for Theoretical Physics in Canada and the California Institute of Technology, often called Caltech, host research programs that explore the deepest foundations of quantum theory. Physicists at these institutions investigate topics such as quantum gravity, quantum information theory, and the relationship between entanglement and spacetime. These efforts seek to answer some of the most profound questions in science. Why does quantum mechanics work so well? What does the wave function truly represent? And how does the quantum world give rise to the classical reality we experience every day? The answers to these questions remain incomplete, yet the continued success of quantum theory suggests that its strange principles are not temporary curiosities. They reflect genuine features of the universe. From the earliest experiments on blackbody radiation to modern quantum satellites orbiting the Earth, the study of quantum mechanics has repeatedly reshaped our understanding of nature. What once seemed like mysterious anomalies have gradually become the foundation of new technologies and new insights into the structure of reality. And as new experiments continue to explore the boundaries of quantum behavior, it is increasingly clear that the story of quantum physics is far from finished. The universe still has many surprises waiting in the quiet mathematics of the quantum world.